Okay, hello everyone. I'd like to start by expressing empathy and condolences to the Israelis, Palestinians among you, those who have friends and family from that area. I personally am one such person, and it's not easy these days. So if you need any support, accommodation, let us know. I know that I do. I know that I was not able even to prepare this one meager lecture that I was supposed to finally give. So I'll do what I can. I'll tell you a little bit about the AEP and mismatched decoding or mismatched compression, and then I'll hand it back to the more capable parts of our teaching staff. So I want to tell you a little bit about the AEP. Okay, that's the asymptotic equipartition property, and how it relates to compression, lossless compression, and the fundamental limits on compression. So, and we're going to do, those of you, and hopefully most of you, who will take 276 in the next quarter, we're going to do this stuff very kind of rigorously, mathematically, concretely. So here, I'm allowing myself to just sort of try and give you the gist, the essence, qualitatively, what this is about. I'm going to spare you the epsilons and the deltas. And in fact, I'm going to do this through just one example, which if you sort of understand the essence of this example, then you really understand the AEP. So let's consider, yes? Okay, bigger, and I can use this, the whole thing? Okay, so up to here? Okay, great, but bigger than this? Okay, so let's consider data, like xn, right? We use this notation for the n tuple, okay? x1, x2, up to xn. So this is an n tuple of data that you want to compress, you want to represent it with bits. And let's suppose that this, again, the simplest non-trivial example is when these guys are generated IID according to some generic random variable x, which let's assume for this example is binary, also binary, and with some, oops, sorry, I forgot the bigger, with some Bernoulli parameter p. Okay, so each one of these components is just generated IID, like fair coin flip. The probability of a 1 for each of these is p. Okay, so that's your source of data that you want to compress. So what do we know then about this n tuple that you'll need to represent? Well, we know that with high probability, right, and this is from the law of large numbers, so this means with high probability, with all likelihood, this n tuple, xn, is going to have a few properties. So let's see. It's going to have, number one, how many, like approximately, so again, these guys are IID, Bernoulli P. So approximately, how many ones am I going to see here? Like, I'm going to see zeros and ones. Approximately, what fraction of these components is going to be ones? P. Right. That's the law of large numbers applied to this case. So, right, approximately, we're going to see n times p ones. Everybody okay with this? And similarly, how many, approximately, right, like, then how many zeros are we going to see here? Right, the remaining places, which is fraction 1 minus p of the places. So approximately n times 1 minus p of the components are going to be zeros. Right? And so number 3, for this sequence that was realized by flipping these coins, I'm going to look at this sequence and ask, oh, in retrospect, what was its probability? So I'm going to ask, and I'm sorry for slight abuse, I mean, this is P that represents the Bernoulli parameter, but this is like bigger P that represents the probability of this realized sequence. Okay, so I'm going to look at this realized sequence, some zeros, some ones, and I'm going to ask, hey, you know, what's the probability of seeing such a sequence? Okay? So that's going to be, right, approximately, right? In fact, before approximately, let's ask ourselves exactly what is this going to be, right? So what's the probability of seeing some particular sequence that has like 0 here, 0, 1, 1, 0, 1, 1, 0. What's the probability of seeing exactly that sequence? What was the attempt?
1 over 2 to the n.
Oh, 1 over 2 to the n. Okay, note that would have been true if p were a half, right? Then all sequences are equally likely. Each has a probability of 1 over 2 to the n. Okay, but now these sequences come with a bias, with a probability of a 1 being p, right? So what's the probability of seeing a particular sequence, 0, 0, 1, 1, 0, 0, 1, 1, if the way that I generated these sequences was IID Bernoulli P?
It depends on the number of ones.
Right? How?
P to the power of k multiplied by 1 minus p to the power of n minus.
Exactly. So it's going to be P. So, you know, this is small p. So it's going to be, in fact, exactly small p, the small p that governs the bias in these coin flips, to the power, let's just write in words, right? Number of ones in this sequence, in xn, right? Times 1 minus p to the power number of zeros in xn, right? Every 1 here gives me a factor of p. Every 0 gives me a factor of 1 minus p. Okay? And so approximately, right, by these two properties, this is going to be then what? P, right? This small p to the power number of ones, right, with high probability is going to be about np. Right? Times 1 minus p to the power of zeros, which with high probability is going to be n times 1 minus p. Right? So That's equal to what? It's equal to, well, I can always write this as 2 to the power log base 2 of the same thing, right? So it's 2 to the power log base 2. When I don't write the base, it's just base 2. 2 to the power log base 2 of the same thing, right? That's p n times p times 1 minus p n times 1 minus p. Right? Which is what? 2 to the power n log of, or I have here the p that comes here, p times log of, in fact, let me do this, 2 to the minus, let me pull out a minus here. So I have p times minus log of p, or in other words, log of 1 over p, plus 1 minus p log of 1 over 1 minus p. Does this look familiar? What is this in terms of a quantity that you recently encountered and defined? Right. This is exactly the entropy of these components, of this random variable x that describes them, right? It's P, right? The entropy. Maybe we should remind ourselves, right? In general, the entropy of a random variable x, right, was defined as the sum over all the possible values, small x, that this random variable can take. Its probability, the probability of the small x, log 1 over the probability. In the case of Bernoulli P, something that has 2 possible values, 1 with probability P, so that's the P log 1 over P, and then the other value, the other possible value 0 that has probability 1 minus P, so that's the other value, 1 minus P log 1 over 1 minus P. Okay, so this is nothing but the entropy of the source, which is generating your data. So, okay, so with high probability, with all likelihood, the sequence that you're going to get is going to have, when you look at it, you're going to ask, oh, what's the probability in retrospect that's the sequence that I got? Well, its probability is about 2 to the minus n times the entropy. Everybody okay with this so far? And so now let's ask ourselves, how many sequences with this property, with this, let's say, with this property, okay, with this. Okay, so how many sequences have the property, right? So this is these are binary sequences, right? Overall we have 2 to the n possible sequences, but how many of them have this property that their probability is about 2 to the minus n h? Is there a question? Okay. Right, so let's let's think about it. Collectively, right, all the sequences with this property, so collectively, their probability is essentially 1, right? Because I said, we talked about how with high probability, right, the law of large numbers tells us that with high probability, with all likelihood, in other words, with probability essentially 1, right, the sequence that we're going to get is going to have this property. Okay? So collectively, all the sequences with this property have probability about 1. Okay? And each of them, but by definition of this property, each of these has this probability. Has probability approximately 2 to the minus n h. So how many such sequences are there, approximately? Right? We've got a collection of sequences, I'm asking about a collection of possible sequences that could be realized, right? Collectively, all the sequences in this collection collectively have probability about 1. And each of them individually has essentially the same probability, about 2 to the minus nh. Right? So how many sequences are there? Must there be in this set that I'm asking about? Right? They each have essentially the same probability, the same small probability. And collectively, the sum of all their probabilities is about 1. Right. Essentially, 1 over their individual probabilities. Right? They each have essentially the same small probability. Let's say epsilon. Right? I'm asking about the size of a set, each component of which has the same small probability, epsilon, and the sum of all the probabilities of the elements of this set is about 1. Right? So the size of the set, so the number of sequences is about 1 over that epsilon. Okay? It's essentially like a uniform distribution on this set that has most of the probability about 1. Okay? So the conclusion is that there are approximately 2 to the n, like basically 1 over this epsilon. So about 2 to the n h such sequences. Okay? And they are called, we call them, they are referred to as typical sequences. Okay, so it slightly depends. We won't get into it here. Again, 276. We'll say more. Sometimes typical sequences we require all these 3 properties, or we require just this. But in any case, it's essentially the same thing. With high probability, because of the law of large numbers, we're going to see, the sequence that we are going to see will be typical. What does it mean to be typical? Well, about, in this case, fraction of p 1s, fraction of 1 minus p 0s, and therefore a probability which is about 2 to the minus nh. Okay? And the set of all such sequences, how many are there? About 2 to the nh. And it's a really small set, right? Because if you think about the set of all possible sequences, right? So here are, right? So this is just a cartoon, okay? So this is the set of all, let's say again, in this example, binary sequences. So this is all binary sequences. Right? How many binary sequences are there, like of length n? Right? How many binary sequences? So among all the possible values that this thing can take, right? How many possible values does a binary n-tuple take? Right? 2 to the n, right? All binary sequences, so the size of the set of all binary sequences is 2 to the n, okay? And in it is a really small, I mean, it's not a baller, I mean, it's, it's a really small subset of the typical sequences, the set of typical sequences, okay, of size essentially 2 to the nh. Okay, which is, so with all likelihood, the sequence I'm going to be dealing with is going to be in this set, in this typical set, okay, which is a minuscule fraction of all the possible sequences, right? Let's see, like about what's the fraction, like how big is this set, right? This set, its size is about 2 to the nh, right? Relative to all the possible binary sequences, right? That's what? It's 2 to the minus n times 1 minus h. In this, again, we're now focusing on our binary example here. Okay, so now the entropy. This is the entropy of the source which is generating our data, right? So this is the entropy of a Bernoulli P random variable, right? And if P is a biased source, if this is not a half, these are not fair coin flips, but this is some P, right, which is not a half, then what can you tell me about the entropy relative to 1? Is it bigger or smaller? Right, smaller. Among all Bernoulli variables, the one that has largest entropy is Bernoulli half. And that's going to have entropy 1. So anything else which is biased will have entropy less than 1. Right? And so if this is not fair coin flips, which entropy is less than 1, the fraction of the typical sequences that you might actually see with any non-negligible probability is an exponentially small fraction of all the possible sequences. Okay, so this is a very big deal. So this is not drawn to scale. This thing is actually minuscule, exponentially small for large n, as n becomes bigger and bigger. And this has a really fundamental ramification for compression, because what it means is that I can and should focus all my coding efforts on this typical set. I should think about how do I actually design a compressor under this assumption, this value assumption that with all likelihood, the sequence I'm going to have to represent, to describe to the decoder, is going to be here in this small set, right? So, in fact, who can suggest, based on this observation, who can suggest a coding scheme that's going to get a compressor, okay, that's going to get us close to the entropy? Anyone? If I know that my source, the sequence that I will have to describe, right? Let's say I knew probability 1 that the sequence that I'm going to have to describe is in this set, whose size is 2 to the n h. How many bits of description am I going to need? Right? If I need to describe, right, one possible sequence or one possible element among a set of a certain size, right? Then as we've seen, essentially up to rounding off the number of bits that I need to basically describe or index the possible elements in a set of a certain size is log the size, right? So if I knew that my sequence for sure is in here, right, I would need essentially log the size of the set, which is essentially n times h bits to describe it. But now I know that with all likelihood it's going to be here, and with some negligible probability it's going to be something else. Then how can I use that to construct a maybe variable length code, variable length compressor that will come close to compressing down to essentially the entropy of the source? Anyone want to try?
If it's inside the set, then the compressed string starts with 1, and then there's some sequence of bits that just enumerate the elements of the set, and we know that's n times 80 bits. And then otherwise, it starts with a 0, and then it's just fully compressed.
That sounds like a pretty good idea. So let me try and recap. So what the encoder is going to output is first basically 1 bit to indicate whether the source sequence is typical, right? To indicate whether the sequence is typical or not, right? So I'm going to see my realized source sequence. I'm going to ask, wait, is it in this set or not? I'm going to first give you output 1 bit to tell you whether or not it's typical. If it's typical, right, then after this first bit, I'm going to use essentially nh bits, because I'm going to use essentially log the size of the typical set bits. That's all I need in order to describe one element in this set. Right? Describe it. That's if it's typical, right? So if it was typical, then the decoder knows now that, okay, we're focusing on, you're describing me now just one possibility from here, and I need just log the size of this set to describe it. But if that bit indicated that it's not here, it's maybe somewhere here, then let's just use, right, the n bits. Let's be wasteful. Maybe we can get away with less, but let's say now, okay, so it's just some binary sequence of length n. I don't need more than, so I'm just going to use n bits to describe it if it's not typical. Okay, so, right, so for this scheme, what is the expected length, the expected number of bits that this scheme will require for encoding, for describing the source n tuple xn, right? So it's essentially right, well, it's going to be, okay, 1 bit. It's going to be definitely no more than 1 bit, right? Just 1 bit to indicate whether a sequence is typical or not. And then, right, plus, with all likelihood, with probability essentially 1, then I'm going to need n times h bits. And then, okay, I also need to account into this expectation the really small probability, let's call it epsilon n. Okay? This is the probability that the sequence is not typical. Okay, on that event, I'm going to need, okay, n bits. Okay, and in terms of then, right, on average, expected number of bits per source symbol, right? So I'm normalizing by the number of source symbols that I'm describing. Right? So this is going to be about h, right? So for n, as n grows, this is going to be, again, this is going to be extremely small, right? Because this is the probability of being atypical. And this is vanishing. So with this kind of scheme, we were seeing that we could get arbitrarily close to like achieving the entropy. Right? As we work with larger and larger blocks of data, everybody okay with this? Okay, so this AEP, by the way, why is this called the asymptotic equipartition property? Because of this property that asymptotic, because it's sort of when n is large enough, so kind of the law of large numbers starts kicking in, then essentially what we have is that all the action happens in like this small subset where effectively we have like a uniform distribution on the typical sequences. They each have probability about 2 to the minus nh. And also, in fact, implicit in this AEP is is the fact that we can come close, arbitrarily close, to compressing with no more than essentially h, the source entropy bits per source sequence per component. But it also actually implies, or let me ask you, could we do better? Potentially, can we do better than h, the entropy? Can we get away with lossless compression with less than h bits per source symbol? And actually, implicit in everything that we just did is the fact that you cannot. Okay, so let's think about this. So can we do better? Okay, so consider, right, any compressor. So you give me a compressor. And let's say that it uses n times r bits on average. Let's say it uses n r bits to describe the source sequence. Okay, so in other words, r bits per source symbol. Okay, so, or let me just say this, that basically any compressor that you give me that uses nr bits, okay, it's going to be able to represent, right, 2 to the nr possible sequences. Right? So now what if R is less than H? Okay, so what if your compressor is using R bits per source symbol when R is less than H, right? Then